Hello everyone, my name is Wang, the first author of this paper. I'm from Institute of Computing Technology. This work was collaborated with Ohio State University, Minnesota University, Baidu USA, and Capital Normal University. The title of this paper is SafeHidden, an efficient and secure information hiding technique using re-randomization. Okay, what's information hiding technique? Information hiding technique is an intra-process memory isolation. It hits an important area, we call it a safe area, at a random location. And it ensures that there is no pointers in the regular memory points to this area. That is mean that attackers could not to leak the pointers to find the location of a safe area. And the safe area is usually designed as small as possible to ensure the very high randomization entropy. Normal access are done through an offset from a dedicated register. This technique is widely used in code reuse defenses, such as CFI, CPI, and code re-randomization. But recently, IH is not secure anymore. There are many attacks had proposed against the information hiding. We classified these attacks into three types. The first type was when memory scanning avoids the crash. This slide gives a user memory space, and there is a safe area hidden in the very large unmapped area, and the base address is stored into the GS segmentation register. Attacker wants to locate safe area. So they use the vulnerability to scanning the memory to find the location of safe area. During memory scanning, it will probe many unmapped areas that could trigger the program crash. So there are two works proposed to avoid the crash. The first is the CLP attack. It uses the exception handling mechanism in JavaScript engine to avoid the crash. The second is clone probing attack. It probes the child process to avoid the crash the parent process, such as web servers. The attacker probes the worker process, and if the worker process is crashed, the daemon process will fork the child process, and the memory layout of the child process is the same to the parent process. Okay, the second type of attacks are reducing the entropy of safe area. There are also two work attack IH. The first one is filling memory safe areas. One work found that some safe areas are implemented as thread local, such as shadow stack and safe stack. So they could spray threads and then spray many thread local safe areas into the memory. The second is filling the memory holes. They allocate memory repeatedly to occupy the unmapped area. So the success probability of probing the safe area is increased. The last one is ANC side channel attack against IH. We know that the normal access to safe area are done through the virtual address. The hardware should perform the address translation from virtual address to the physical address by working a page table. There are these full level page tables. There are full PTEs. During page table working, these full PTEs will be loaded into the last level cache, so that attacker could perform the cache-based side channel analysis to infer the location of PTEs, and finally find the location of safe area. So I have reviewed all the attacks against the information hiding. The next we will give the Strand model of our work. We consider an IH-based defenses that protects a vulnerable application against code reuse attacks, such as web servers or browsers. The design of this IH-based defense is not flawed. Before launching code reuse attacks, attackers must compromise the defense by reviewing the safe errors. Attackers have 3 abilities. First is read and write arbitrary memory locations. The second is allocate and free arbitrary memory areas. The last is create any number of threads. We reviewed all known attacks and summarized them into 4 attack vectors. Vector 1, gathering memory layout information to help to locate safe error. We know that during memory scanning, the attacker needs to know the probe address is mapped or not. If it is mapped, they should judge if the mapped area is safe area or other data area or code area. The second vector is creating opportunities to probe without crashing the system. The third is reducing the entropy of the randomized safe error locations. The last is monitoring page table access patterns using catch side channels. Okay, the next slide will give our design. SafeHidden. SafeHidden is proposed to block all these attack vectors. It intercepts all types of probes that may leak the locations of safe error. It randomizes safe errors upon detecting suspicious probes, isolating the threat local safe errors, and raising security alarms when illegal probes are detected. Okay, let's see how SafeHidden block these attack vectors. To block vector 1, SafeHidden intercepts all the events that may be triggered by the attackers. For some are memory management system calls, such as IMAP, protect, and BRK. Attackers could use this system call to scanning the memory or filling the memory holes. The second is system calls that could return e-fault value. It could use system calls to scanning the memory without crash the system. The third is cloning memory space. The last is memory access instructions. SafeHidden didn't instrument all memory access instructions because normal access instructions only access the mapped area, that is code area and the data area. But these memory access instructions reused by attackers maybe access the unmapped area during memory scanning. So SafeHidden only intercepts the page fault exception in the unmapped area. The left part gives the picture of how SafeHidden block it. I'm sorry. During memory scanning, SafeHidden will randomize the safe error's location. But we know that the re-randomization only increases 1 bit randomness. So the persistent attacks could always succeed. That's the vector 2 we need to block. To block vector 2, SafeHidden leave traps at the original location of safe errors after randomizing the safe error. During memory scanning, SafeHidden will create many trap errors, and the attacker will be captured by the trap errors more likely. The third is reducing the entropy of the randomized safe error locations. SafeHidden prevents unlimited shrink of unmapped areas and unrestricted growth of safe errors. The maximum size of the mapped area is set to 64 TB, which is half of the user memory space. The second, it uses a thread private memory mechanism to isolate thread local safe errors. The entropy will not be reduced by thread spraying. This is because attackers could not access other thread local safe errors in one thread. In particular, we use hardware-assisted virtualization technique, that is extended page table, to achieve this mechanism. All threads will share the same page tables, but each thread will be assigned a thread private EPT. But more details about this mechanism are in our paper. The last vector is the side channels. we have two observations about this attack. It needs hundreds of pre-improv or EVC time tests. It's also imperative that the addresses of the PTEs corresponding to this memory area are not changed during tests. That is to say, the cache entries mapped by these PTEs are not changed too. So the solution is the same. We use re-randomization. SafeHidden also monitors legal access to the safe area that may be triggered by the attacker on purpose. Once such legal access is detected, SafeHidden will randomize the location of the safe area. But how to detect this legal access from the attacker is the problem. The key step of cache side channel attack against the page table is to force a page table walk. We knew that if TRB hit, the virtual address will be translated to the physical address directly, so the attacker must trigger the TRB miss. So we could intercept the TRB misses to intercept the possible probing. But how to only intercept the TRB miss occurred in safe area is a problem. We know that Intel provides PMU to sample the TRB misses, but it is not accuracy, and it only samples the whole process. The processes TRB misses. Our solution is convert TRB miss to page fault exception by using the architecture support. This is a PTE format. There are 4 bits are reserved bits. When the reserved bit is set, a page fault exception will be triggered during the page table walk. SafeHidden sets the reserved bit in all the PTEs for the safe areas to detect the TRB misses. When a TRB miss occurs, it's trapped into the page fault handler. Okay, let's give the flowchart of page fault handler. If TRB hit, virtual address will be translated to the physical address directly. If TRB miss, hardware will perform page table walking and the possible triggering page fault exception, and the SafeHidden intercept its exception and check if the reserved bit of the corresponding PTE is set or not. If it is not set, it will deliver the control flow to the original page fault handler. If it is set, it means that this exception is a fake page fault exception we need to handle. First, we will clean all safe areas reserved bits and perform one round randomization of safe area, and then preload the PTE of fault address into TRB and set reserved bits of reserved bits in all the PTEs and relocate the fault address to the new address and return to user. But there are 2 problems here. The first is how to preload the PTE into TRB under the KBTI technique. We know that to mitigate meltdown attack, Linux kernel integrated the KBTI technique. It splits the page table into kernel mode page table and the user mode page table. Our SafeHidden, because our SafeHidden needs to intercept the system call and the page fault exception, so SafeHidden is mapped into the kernel mode page table. And it needs to preload the user mode page table PTE into TRB. During context switch, it will switch the page table and will flush the TRB. How to preload the user mode PTE in the TRB is a problem. The second is it could cause many false alarm TRB misses at a new location. We know that in this flowchart, at any time there is only one PTE of safe error loaded into the TRB. That breaks the access locality of safe error and incurs very high performance overhead. We need to handle this. More about this are detailed in our paper. Okay, let's see the system implementation. SafeHidden is designed as a loadable kernel module. We integrated a thin hypervisor for a non-virtualized OS. It virtualizes the running OS as a guest without rebooting the system. The other components called guest KM runs in guest kernel. This is the architecture overview. There are 2 great parts. First is guest kernel module. The last is hypervisor. SafeHidden intercepts the system calls and page fault exception and check if it is need perform randomization or raising security alarm. And SafeHidden also maintains the EPTs to achieve thread private memory mechanism. Illegal access to the thread local safe area will trigger EPT violation exception and captured by the hypervisor, and hypervisor inject this exception into the guest kernel module, and the kernel module raises the security alarm. Okay, let's give a performance evaluation. SafeHidden is implemented on x86-64 Linux platform. SafeHidden protects two devices that are using IH, that is shadow stack and OSFI. And the GS segmentation register is used to point to the safe area. We chose 3 types of benchmarks to evaluate. One is CPU-intensive benchmarks, such as SPEC and PASEC. The second is network I/O benchmark, such as NGX and Apache. The last is the disk I/O. We use Bernie benchmark 2. For CPU-intensive benchmarks, for SPEC, SafeHidden incurred less than 3% performance overhead when protecting OSFI and shadow stack, and incurred around 6% performance overhead when protecting OSFI and shadow stack. The reason why SafeHidden incurred higher performance overhead in multi-threaded benchmarks, that is because SafeHidden needs to maintain the EPTs to isolate the thread local safe areas. The second is the network I/O benchmark. For Apache, SafeHidden incurred around 12% performance overhead when protecting OSFI and shadow stack. And for NGX, it incurred less than 6% performance overhead. Also, the SafeHidden incurs very high performance overhead in multi-thread benchmarks. The last is disk I/O benchmark. SafeHidden incurs less than 3% performance overhead. That gives the conclusion. SafeHidden proposed the randomization-based IH technique against all known attacks, and it introduced the use of thread private memory to isolate thread local safe areas, and devised a new technique to detect TLB miss. Thanks. Any questions?
So I'll go ahead and ask one here while they're coming up. So I'm curious as to why you chose to use EPTs rather than, let's say, just unmap and create multiple address spaces for each thread, for the thread local area. Wouldn't like the KPTI already kind of hide the cost because you're already having to switch?
Do you mean why we use hardware virtualization technique?
Yeah, instead of just separate address spaces at the operating system level.
This is due to we want to compatible with the Linux kernel, because another way to implement thread private mechanism, thread private memory mechanism is to use each thread as a page table. But the CPU when hardware working the page table, it will set the reserve, it will set the access bit and dirty bits. But synchronizing all these bits in one page table is a problem.
Okay.
So in our implementations, all threads use one page table as normal.
Okay, that makes a lot of sense.
Yeah.
Thank you.
Hi, John Crizzle, University of Rochester. So one question I have is a bit of a higher level question. When you have a diversification or randomization-based defense, right? You have the issue of an attacker trying to attack the system over and over and over again with random guesses, right? So if they can't deduce where things are at, they can just keep guessing, right? So, which means that at some point they'll get lucky and guess the correct answer, right? So my question is, you have this security alert, right, that's supposed to stop the attacker, right? They've been detected, but what is an administrator or system supposed to do once an attack is detected to make the attack go away?
Do you mean how SafeHidden handles the security alarm?
Well, so my question is you get a security alarm, then what? What are you supposed to do with that information? Either the system or the system administrator.
If SafeHidden captured the attackers, it raises the security alarm. But for application scenario, we have different handling. For example, for web servers, SafeHidden could be integrated into the firewall to forbid them to access that IP. For web servers, browsers, SafeHidden can be integrated into browser to forbid them to download the JS code, JavaScript code from that website.
Okay, so basically it's an application-specific sort of reaction to the attack.
Yeah, yes.
Okay, thanks.
We'll do one more question from second mic while our next speaker comes and gets set up.
On your spec benchmarking, did you turn off ASLR, and how many iterations of the spec benchmarks did you run?
Oh, I'm sorry, I can't understand what you.
Sorry, Drew Dean, Amazon. When you did the spec benchmarks, did you turn off address space layout randomization?
You mean the?
So ASLR is typically turned on, and did you disable it for your evaluation?
The TRV misses count?
No, just ASLR. Let's go ahead and take it offline. We got to get moving. So, all right, let's go ahead and thank our speaker once again.